What if I told you that in 1969 a completely stock Chevrolet Camaro was running quarter-mile times that should have been physically impossible? Not just unlikely, not just impressive, mathematically impossible, based on every law of physics and every performance calculator known to man. This wasn't some factory ringer or a secretly modified car. This was a bone-stock, numbers-matching Camaro that any dealer could order. Yet it was consistently running times that made veteran racers question their stopwatches. And picture this. It's a humid Saturday night at Lyons Drag Strip in Long Beach, California. The year is 1969. The muscle car wars are at their absolute peak. Every manufacturer is lying about horsepower ratings, either inflating them for marketing or deflating them for insurance. Everyone's playing games with the numbers. But at the staging lanes, a primer gray Camaro rolls up that's about to make everyone question what they thought they knew about going fast. The driver? A 34-year-old mechanic named Tommy Ivo, not the famous TV Tommy Ivo, but a soft-spoken transmission specialist from Pomona who worked out of a two-bay garage behind a Sinclair station. This is the story of how one mechanic discovered something that Detroit's best engineers had overlooked, something that would challenge everything the racing community believed about making power, and something that would eventually influence how every serious drag racer approaches their craft today. Tommy didn't add a single horsepower to that Camaro. He didn't touch the engine internals. He didn't even change the rear gear ratio. What he did was far more clever, far more subtle, and according to the physics textbooks of the time, shouldn't have worked at all. To understand why Tommy's discovery was so revolutionary, we need to travel back to the golden age of American muscle. By 1969, the horsepower wars had reached a fever pitch. Dodge was stuffing 426 HEMAS into everything that moved. Ford had the Boss 429. Pontiac was dominating with the Ram Air 4. And Chevrolet? They had the L78 396 Big Block, officially rated at 375 horsepower, but widely known to make closer to 425 at the crank. It was a solid engine, a good engine, but nothing special in the brutal world of superstock drag racing. And then the drag racing scene in Southern California was the epicenter of straight-line performance innovation. Every weekend, thousands of racers would converge on strips like Lyons, Irwindale, and Orange County International Raceway. These weren't just casual racers. These were serious competitors with serious money on the line. Class racing was incredibly competitive, with wins often decided by thousandths of a second. Everyone was looking for an edge, and most of them found it the traditional way: more compression, bigger carburetors, steeper gears, better tires. Tommy Ivo approached things differently. He'd spent 15 years rebuilding transmissions, and he'd noticed something peculiar. The cars that came back with the least transmission damage weren't always the ones driven gently. They were the ones where power delivery was smoothest. Not less power, but smoother power. He'd rebuilt enough broken Turbo 400s and Muncie 4-speeds to recognize the pattern. Violent, jarring shifts might feel fast, but they were breaking more than just transmission parts. The problem Tommy identified was something physicists call impulse loading. When you dump the clutch or hammer the throttle, you're not just applying force, you're applying it instantaneously. That sudden shock has to go somewhere. It travels through the drivetrain like a shock wave. The drive shaft twists, the differential gears flex, the axles wind up like springs. And here's the critical part. While all that's happening, while all those components are absorbing and releasing that energy, the tires are breaking loose. Not just spinning, but actually bouncing off the pavement, microscopically, hundreds of times per second. The conventional wisdom in 1969 was simple. Power equals speed. More power equals more speed. If your car wasn't fast enough, you needed more horsepower, period. The entire aftermarket performance industry was built on this premise. Edelbrock sold intake manifolds that promised 20 extra horsepower. Hooker headers claimed another 15. Mickey Thompson was selling slicks that could handle 500 horsepower. Everyone was chasing bigger numbers. But Tommy had access to something most racers didn't: a high-speed camera borrowed from his brother-in-law who worked at Hughes Aircraft. This wasn't some handheld 8mm camera. This was a genuine high-speed unit capable of 1,000 frames per second, the kind they used to film rocket tests. Tommy set it up at the starting line, focused on the rear tires of various cars as they launched. What he saw changed everything. The fastest cars weren't necessarily the most powerful. They were the ones whose tires stayed in contact with the pavement longest during the critical first 60 feet. A car making 375 horsepower that kept its tires hooked would beat a 425 horsepower car that spent the first second bouncing and spinning. It wasn't about peak power, it was about usable power. And the difference between the two was massive. Winner and Tommy bought his test car for $2,800 from a Chevrolet dealer in Alhambra. It was an L78 Camaro, rally green with black stripes, 4-speed transmission, 3.73 rear gears, completely stock except for a set of M&H Racemaster slicks that everyone in the class was running. The car's first pass down the strip was disappointing, but expected: 13.42 seconds at 102 miles per hour. Respectable for a stock L78, but nothing special. Cars with the same engine were running anywhere from 13.2 to 13.6, depending on driver skill and atmospheric conditions. 10 Schwanzmann, that's when Tommy started implementing his theory. But here's where it gets interesting. He didn't add any parts. He started removing them, or more accurately, he started softening them. The first modification was so simple that other racers laughed when they saw it. He drilled 3/4-inch holes in the clutch disc springs. Not enough to weaken them significantly, just enough to change their rate of engagement. The clutch would now slip for approximately 0.3 seconds longer during launch. And next, he turned his attention to the drive shaft. The stock unit was a hefty steel piece designed to handle the L78's torque with a massive safety margin. Tommy had a new one made, not from exotic materials, but from thinner wall tubing. It was the same diameter, same length, but about 30% more flexible in torsion. When torque was applied, it would twist slightly, absorbing the initial shock like a torsion bar. The differential was next. A stock 12-bolt Chevrolet rear end came with heavy-duty spider gears designed to handle 500 pound-feet of torque without braking. Tommy replaced them with earlier model pieces from a 1965 Chevy, gears that were known to be slightly less robust but had more backlash, more free play. He shimmed them to the loosest acceptable tolerance, adding almost a full degree of rotational play. And for the motor mounts, instead of using solid race mounts like everyone else, Tommy went the opposite direction. He found a set of 1967 Chevelle 6-cylinder motor mounts, the softest ones GM made. They were designed for a 194 cubic inch inline 6, making 120 horsepower. Putting them under an L78 big block seemed like insanity. Other racers warned him the engine would tear itself out of the car. The transmission mount got similar treatment. Tommy fabricated a custom mount using a material nobody in drag racing had heard of: sorbothane. It was a viscoelastic polymer developed by British Petroleum for dampening vibrations in North Sea oil platforms. His brother-in-law had brought home a sample from Hughes Aircraft, where they were testing it for satellite isolation. The material was almost magical in its ability to absorb shock while still transmitting steady force. And even the rear suspension got the treatment. Instead of using the typical drag racing setup of super stiff rear springs and pinion snubbers, Tommy installed softer springs from a base model 6-cylinder Camaro. He adjusted the rear shocks to their softest setting. He removed the front anti-roll bar entirely and disconnected the rear bar. The car now had so much body roll that it looked like a 1950s taxicab going around corners. The first test, with all modifications in place, happened on a Thursday evening at Irwindale. Tommy wanted to test without an audience, without the pressure of competition. He staged the car, brought the RPMs up to 3,500, and dumped the clutch. What happened next was unlike any Camaro launch anyone had seen before. Instead of the violent tire-smoking launch typical of big block cars, the Camaro seemed to ooze forward. The tires chirped once, bit, and the car began accelerating with an almost turbine-like smoothness. Nen. The time slip told the story, 12:91 seconds at 104 miles per hour. Tommy had just knocked half a second off his ET while gaining only 2 miles per hour in trap speed. That's when the physics gets really interesting. Trap speed is primarily determined by horsepower. ET is determined by how effectively you use that horsepower. The car wasn't making any more power, the trap speed proved that, but it was using its power far more efficiently. But wait, there's more. The real magic wasn't in the overall ET, it was in the incrementals. The car's 60-foot time had dropped from 2.1 seconds to 1.78 seconds. That's where the entire improvement came from. From 60 feet to the finish line, the car was actually slightly slower than stock because of the softer setup. But that blazing launch more than made up for it. And then Tommy spent the next 3 weeks fine-tuning his setup. He experimented with different clutch engagement rates, varying the hole sizes and spring tensions. He tried different drive shaft wall thicknesses. He even had 3 different sets of differential gears shimmed to different tolerances. Every change was logged in a notebook with corresponding weather conditions, track temperature, and resulting times. The optimization process revealed something crucial. There was a sweet spot, a perfect amount of compliance in the drivetrain. Too stiff, and you got wheel spin from the shock loading. Too soft, and you lost power through drivetrain windup. The ideal setup had just enough give to keep the tires hooked, but not so much that energy was wasted. It was like tuning a guitar string. There was one perfect tension that made everything resonate correctly. Engine. By the time Tommy entered his first real competition at the Hot Rod Magazine Championships at Riverside International Raceway, he had the setup dialed in perfectly. The car was now consistently running 12.85 to 1290, times that should have required at least 425 horsepower, according to every performance calculator. Remember, this was a bone stock L78, making maybe 375 at the wheels. The math didn't add up. The racing community's reaction was immediate and skeptical. After Tommy won his class qualifying with a 1286, rumors started flying. He must have a ringer engine. There must be nitrous. Something had to be illegal. Tech inspection tore the car apart. They checked displacement, compression, cam specs, everything. It was stone stock. They even made Tommy remove the valve covers so they could verify the valve springs. Everything checked out. The controversy intensified in eliminations. Tommy's Camaro was paired against a documented L88 Corvette, a car making at least 50 more horsepower. The Corvette driver, a veteran racer named Dick Moroso, was confident. His car had run 12.7s all day. The race shouldn't have been close, but when the tree dropped, Tommy's Camaro launched like it was attached to a cable. By 60 feet, he had 3 car lengths. The Corvette was closing fast, its superior power showing, but it was too late. Tommy won by half a car length, running a 12.83 to the Corvette's 12.92 odds. The tech inspectors went even deeper this time. They pulled spark plugs to check for nitrous residue. They checked the fuel for additives. They even borrowed a bore scope from a local aircraft mechanic to inspect the intake ports for illegal porting. Nothing. The engine was box stock. That's when people started paying attention to what Tommy had actually done. The physics behind Tommy's setup was elegant once you understood it. Every component in a drivetrain has a resonant frequency, a speed at which it naturally wants to vibrate. In a typical drag car with stiff everything, all these frequencies are high and close together. When you dump the clutch, you excite all of them simultaneously. It's like hitting every key on a piano at once. You get noise, not music. Tommy's soft components shifted these resonant frequencies lower and spread them apart. When the clutch engaged, each component absorbed the shock in sequence, not simultaneously. The clutch disc compressed first, then the motor mounts flexed, then the drive shaft twisted, then the differential gears took up their backlash. Instead of one massive shock, the tires experienced a series of smaller impulses spread over nearly half a second. The total energy was the same, but the peak force was dramatically lower. And then think about it like this. If someone throws a baseball at your chest, it hurts. But if they throw the same baseball at the same speed into a pillow you're holding, you barely feel it. The pillow doesn't reduce the baseball's energy. It just spreads that energy over time. That's exactly what Tommy's modifications did. They turned the entire drivetrain into a mechanical pillow that cushioned the tires from the engine's violence. The data supported this theory perfectly. Using borrowed equipment from Hughes Aircraft again, Tommy's brother-in-law helped him instrument the car with strain gauges and accelerometers. They measured forces throughout the drivetrain during launches. A stock setup showed peak loads of over 4,000 pound-feet at the axles, lasting about 0.1 seconds. Tommy's setup never exceeded 2,800 pound-feet, but maintained 2,000 plus for nearly 0.4 seconds. Lower peak, longer duration, same total energy transfer. The tire data was even more revealing. High-speed photography showed that stock cars' rear tires actually left the pavement completely during hard launches, bouncing like basketballs in slow motion. The contact patch would shrink to almost nothing, then slam back down, then lift again. This cycling could happen dozens of times in the first second. Tommy's car? The tires squatted, spread, and stayed planted. They never fully broke loose, never bounced, just steadily transferred power to the pavement. Hans and other racers started trying to copy Tommy's setup, but most missed the crucial details. They'd soften one component but leave others stock. Or they'd go too soft everywhere and end up with a car that felt like it was made of rubber bands. The secret was in the system, not any individual component. Everything had to work together, had to be tuned as a complete package. The most common mistake was the clutch. Racers would drill their clutch discs, but they'd drill too many holes or make them too large. The clutch would slip too long, generating heat and losing power. Tommy's setup slipped for exactly 0.3 seconds, just long enough to cushion the initial hit, but not long enough to waste energy. He actually went through 11 different clutch discs to find the perfect modification. None the automotive press eventually picked up the story. Hot Rod magazine sent their technical editor, Eric Dahlquist, to investigate. Eric was skeptical, a trained engineer who understood the physics involved. He brought his own test equipment, his own stopwatches, even his own weather station to ensure accurate density-altitude calculations. After 3 days of testing and analysis, his conclusion was unequivocal. Tommy's system worked exactly as claimed. The article, published in the March 1970 issue, was titled, "The Soft Touch Revolution." It explained Tommy's theories in detail, complete with graphs and charts showing the force measurements. The response from readers was immediate and polarizing. Traditional racers called it nonsense, insisted that stiffer was always better. But a new generation of racers, particularly those running in stock and super stock classes where modifications were limited, saw the potential. Within 6 months, the concept had spread throughout the drag racing community. Lakewood Industries introduced a Sheichau's soft low-kiema clutch disc with built-in compliance. Moroso created a Haus Flexi Shaft Joe drive shaft designed to twist under load. Strange Engineering developed a Saus cushion gears for differentials. The entire industry was adapting to Tommy's discovery. But here's where the story takes an interesting turn. General Motors engineers had known about this phenomenon all along. Internal documents from the late 1960s, declassified decades later during a patent lawsuit, showed that GM's powertrain division had extensively studied drivetrain shock. They understood that softer components could improve launches. So why didn't they implement it from the factory? And the answer was durability. Those soft components that worked so well for drag racing would never survive 100,000 miles of street driving. The clutch discs would wear out in months. The soft motor mounts would sag and fail. The flexible drive shafts would develop harmonic vibrations at highway speeds. GM's engineers had to design for longevity, not just straight-line performance. They chose durability over acceleration, a reasonable decision for street cars. Onstjarnes, this revelation actually validated Tommy's approach even more. He wasn't discovering something new so much as rediscovering something that had been intentionally engineered out of production cars. He was optimizing for a completely different use case, one where components could be replaced frequently and comfort didn't matter. The influence of Tommy's discovery extended far beyond drag racing. NASCAR teams started experimenting with drivetrain compliance to improve corner exit acceleration. Road racers found that softer driveline components could improve traction in the rain. Even Formula One teams began incorporating flexible elements in their drivetrain designs, though they used exotic materials like carbon fiber instead of simply softening steel components. And modern drag racing has taken Tommy's concepts to extremes he never imagined. Today's pro stock cars use multi-disc clutches with precisely engineered slippage curves. Drive shafts are made from carbon fiber with specifically tuned torsional frequencies. Differentials use sophisticated limited slip mechanisms that provide exactly the right amount of cushioning. The entire drivetrain is now viewed as a shock absorption system first and a power transmission system second. And the mathematical models have gotten incredibly sophisticated. Racing teams use finite element analysis to simulate every component's behavior under load. They can predict exactly how much a drive shaft will twist, how long a clutch will slip, how much a tire will deform. What Tommy figured out through trial and error is now calculated to the 0.1% before parts are even manufactured. But the fundamental principle remains unchanged. Power without traction is just noise and smoke. The trick isn't making more power, it's delivering the power you have more effectively. A modern pro stock car makes over 1,500 horsepower, but it uses Tommy's principles to put every single one of those horses to the ground. The clutch still slips, the drive shaft still twists, the differential still cushions. It's just all happening with space-age materials at forces Tommy could never have imagined. And the economic impact was substantial too. The aftermarket performance industry, which had been focused almost entirely on adding power, suddenly had a new market: managing power. Companies that had never made racing parts started developing specialized components. Industrial damper manufacturers found themselves supplying drag racers. Material scientists who'd been working on aerospace applications were suddenly consulting for race teams. And Tommy himself never got rich from his discovery. He didn't patent anything, didn't start a company, didn't even write a book. He continued working as a transmission specialist, eventually opening his own shop in Fontana. But every serious racer in Southern California knew his name. He became the go-to guy for drivetrain setup, the wizard who could make a slow car fast without adding a single horsepower. And the Camaro that started it all? Tommy kept it until 1983, racing it occasionally, but mostly using it as a test bed for new ideas. He sold it to a collector who promised to keep it exactly as Tommy had set it up. Today, That car sits in a private collection in Scottsdale, Arizona, still wearing its primer gray paint, still with those drilled clutch discs and soft motor mounts. It's a rolling monument to the power of thinking differently. And what made Tommy's discovery so revolutionary wasn't just that it worked. It was that it challenged the fundamental assumption of racing, that more is always better. Sometimes less is more. Sometimes soft beats hard. Sometimes the solution isn't to overcome physics, but to work with it. Every modern drag car that uses progressive clutch engagement, every drive shaft designed to twist under load, every differential shimmed for controlled slippage, they're all descendants of Tommy's rah-rah's weird trick. The lesson extends beyond racing, beyond cars, beyond engineering. It's about questioning assumptions, about looking at problems from different angles, about understanding that brute force isn't always the answer. Tommy didn't have the budget of General Motors or the resources of a major racing team. He had curiosity, persistence, and the willingness to try something everyone said wouldn't work. And modern electric vehicles are actually returning to Tommy's principles in unexpected ways. Tesla's ludicrous mode doesn't just dump all available power to the wheels. It uses sophisticated algorithms to manage power delivery, preventing wheel spin while maximizing acceleration. The system monitors wheel speed hundreds of times per second, adjusting power to maintain optimal traction. It's Tommy's mechanical solution implemented electronically, but the principle is identical. Smooth power delivery beats raw power every time. Next, the racing world has never forgotten Tommy's contribution. In 2018, he was inducted into the International Drag Racing Hall of Fame, not as a driver, but as an innovator. At 83 years old, he attended the ceremony in his original Sinclair Station coveralls. His acceptance speech was typically modest. "I just wanted to go faster without spending money on engine parts." Turns out the answer wasn't under the hood. What's time today's racers have tools Tommy could only dream of. Data acquisition systems that measure every parameter thousands of times per second. Computer simulations that can predict performance before parts are built. Materials that didn't exist in 1969, but they're all trying to solve the same problem Tommy solved with drill bits and junkyard parts. How to transfer power from engine to pavement as efficiently as possible. The next time you watch a modern drag race, pay attention to the launches. Notice how the fastest cars don't leave in a cloud of tire smoke. Watch how they squat, grip, and accelerate with an almost electric smoothness. That's Tommy's legacy. Every one of those cars is using some version of his discovery, refined and perfected over 5 decades, but fundamentally unchanged. The soft touch revolution changed more than just drag racing. It changed how engineers think about power transmission in every application. Industrial machinery now uses similar principles to reduce shock loads. Wind turbines incorporate drivetrain compliance to handle gusty conditions. Even the Mars rovers use flexible couplings in their drive systems, lessons learned from drag strips applied to other planets. So what's the takeaway from this story? Maybe it's that innovation doesn't always require advanced degrees or massive budgets. Sometimes it just requires looking at an old problem in a new way. Tommy Ivo saw what everyone else missed, not because he was smarter or better educated, but because he was willing to question what everyone knew to be true. In a world that often celebrates the biggest, fastest, strongest, and most powerful, there's something beautiful about a story where finesse beats force, where thinking beats spending, where a mechanic with grease under his fingernails outsmarted teams of engineers with unlimited budgets. It's a reminder that in racing, as in life, the obvious answer isn't always the right answer. And on that primer gray Camaro running impossible times wasn't just a race car. It was a rolling proof of concept that challenged everything the racing world believed. And Tommy Ivo? He wasn't just a mechanic who figured out a weird trick. He was an innovator who revolutionized an entire sport by doing the opposite of what everyone else was doing. In the end, That's what real innovation looks like, not following the crowd to extremes, but finding a completely different path to the same destination. Nanen, what's your own hard impossible story? Have you ever seen something that shouldn't work but did? Drop a comment below and share your experience. And if you enjoyed this deep dive into drag racing history and innovation, make sure to subscribe, because we're just getting started exploring the stories of automotive legends who changed the game.